lesson we are going to be talking about geometry trains. By this we mean shapes that are linked together to kind of form a train, and it's going to be a repeating pattern, and we're going to pretend that they are formed out of toothpicks and count how many toothpicks there are. We're going to do this in two ways. We're going to do it once where we just count the outside, and once where we count the perimeter or total, and once where we count the total. So I'm going to mark perimeter here, total here for a second. Oops, there we go, total. So the diamond one is not maybe the best one to start with, the two examples here, but perimeter, how many toothpicks are on the perimeter of this? There are 4. How many toothpicks are on the perimeter of this one? There are 8. And how many toothpicks are on the perimeter of this one? 12. Okay, so you can quickly follow that. What about the total? Well, it happens to be the same for the diamond train, 4, 8, and 12, because there's no toothpicks that are on the interior of the train that are not on the perimeter of the train. Okay, so we're starting to maybe notice a pattern there. Let's see if we start noticing a pattern on the square. So we have perimeter and total, and okay, perimeter I see 4, total I see 4. Okay, well, this time perimeter, if we count the outside 1, 2, 3, 4, 5, 6 in the perimeter, but there are a total of 7 because there's one in the middle that's not counted. Okay, so there we see a difference. And then for train 3, we see 3 on top, 3 on the bottom, and left and right gives us 8. But for the total, there are 2 more that we didn't count, so there's a total of 10. So we might notice 2 separate patterns for the perimeter and the total. So we can continue this for the triangle train and the hexagon train, but let's jump ahead and talk about the results and looking for some formulas. So I'm going to jump to the next worksheet here. Okay, so this is the worksheet that you can record all your data in, but I'm going to jump to this one, which, spoiler alert, has all the answers. Okay, so hopefully you took some time to do this already, but here we're going to go through each train. So these 2 are for the diamond train. So you could have made a table that would have had trains 1, 2, 3, 4, 5, 6, 7, and then train N, an unknown number of trains, and then train 50, something that would be hard to build, but we can use a formula to figure out. So the pattern on the perimeter was going up 4, 8, 12, 16. So you should have seen this adding 4 pattern, and hopefully develop the formula that 4 times n is going to give us the total, the number of toothpicks in the perimeter. So we can use that 4n to figure out 50. So 50 times 4 gives us our 200. Now it's the exact same story for the total toothpicks for the diamond train. As we said, there's the same number in the perimeter as in the total. Great. Let's now talk about the square train. So for the square train, the perimeter goes 4, 6, 8, 10, 12, and we see this adding 2 pattern over and over and over again. And so because there's an adding 2 pattern, we've talked about this when we talked about ratio tables way back. We're going to see a multiplying by 2 factor. But if we try multiplying any of these numbers by 2, the train number by 2, we don't get the total number of toothpicks. So each time here, you might notice that if we multiply the train number by 2, we actually get 2 less than the toothpicks. So what we need to do is tack on a plus 2 to make our formula work. So 2n plus 2 would be the formula for the perimeter toothpicks for the square train. And then we can use that for train 50. 50 times 2 plus 2 is 102. Now for the total, we see an adding 3 pattern, and our formula is 3n plus 1, 151 toothpicks for 50 trains. Oops, did I start on the second 2? Okay, so here's the other ones. For the triangle train just goes up by 1 for the perimeter. So plus 1, but if you just look at them, what's the relationship here is that there's always 2 more toothpicks in the train number. So n plus 2 is our formula. So for the 50th train, 52. But for the total toothpicks, we're going up by 2 every time, and that just multiplying by 2 doesn't quite get us there, so we need to add 1 as well. So 2n plus 1 leads us to figure out that for train 50, there would be 101 toothpicks. All right, and finally for the hexagon train, we see a pattern of going up by 4. And our formula is 4n plus 2. So multiply, for example, 7 times 4 would give us 28. That's 2 short. So we need to add 2 more. So for train 50, times 4 is 200. Add 2 to 202. And then for the hexagon, we see a pattern where we go 6, 11, 16. We're adding 5. We see our formula is 5n plus 1. And so multiplying 50 times 5 is 250 plus 1, 251. Great. So those are the formulas, and I hope that was not the most difficult part of the lesson in finding the formulas. We've done a lot of tables and writing formulas from them. So let's continue here. All right, so now let's talk about some of the things that we might have concluded about this. Okay, so just try to make it bigger there so we can see it. Great. So if we are looking at the 4 rules, let's go ahead and throw them all here in one space. Now we are just talking about total toothpicks here. We could talk about the perimeter toothpicks as well, but let's just stick with the total toothpicks. That's enough information for us to look at here. So for the diamond train, the diamond rule is 4n. And for the triangle train, it is 2n plus 1. And for the square, it was 3n plus 1. And for the hexagon, it was 5n plus 1. So if we look at each geometry train and highlight the toothpicks that were added from the previous train, okay? So in the diamond, for instance, I'm going to draw, oh my goodness, train 2. Okay, there's train 2. So of these toothpicks, which ones were the new ones that were added? So this one was new, this, and this. Okay, so in the diamond, 4 toothpicks were added new in the next one. Okay, great. Now if we look at the square, this is step 2 as well. So if we look at the ones that were added from step 1, this one, and this one. So maybe we should be writing this down. In the diamond, 4. In the square, 3. Let's see if we notice any more patterns. For the triangle, make sure I don't goof this there. That would be step 2. And the ones that were added were these 2. Great. So we've got 2. And then for the hexagon, I need to look at the picture here simultaneously and see if I can do this. Boom. So there's one hexagon, and then I'm cheating, I'm scrolling back here to look at the hexagon. Oh, okay, never mind. If I draw it slightly differently, it'll be better for us here, so let's try that again. I need to draw the flat side over there. Okay. Okay, so let's put the point there, flat side there, so that we can join the flat sides together. Okay, so there's step 2, and 1, 2, 3, 4, 5. Okay, so there are 5 new toothpicks. So we're looking for a connection between the highlighted toothpicks and the rules. Okay, so diamond, square, triangle, hexagon. Pausing for you to make some connections here. Hopefully you're seeing that in the hexagon, there is a 5 in its rule. There is a 5 new highlighted toothpicks. In the triangle, 2 highlighted toothpicks. There is a 2 there. In the square, 3 new toothpicks. 3 in the formula. In the diamond, 4 new toothpicks. 4 in the formula. You might have even noticed something more specific than just there's number is somewhere in the formula. That number is in a specific spot in the formula. The number of new toothpicks is the vocab word, right, from before, coefficient in each rule. So that might have been a little bit tricky if you were unclear about what it was saying, but hopefully you could make that connection. It's an important distinction that the new ones, the ones we're adding each time, turn out to be the coefficient. Okay, so what about the non-highlighted ones? So if you look at each of your train 2s and look at the toothpicks that are not highlighted, what is the connection between the non-highlighted toothpicks and the rules that you listed in question 1? So this is probably where there might have been some confusion. So I'm going to add another color here and use the same pictures here. So almost imagine that we added 4 here, but even in the step before, we like kind of added 4. We kind of see this group of 4 here and a group of 4 here. And here, yes, we added 3 for train 2, but you can almost imagine that we added 3 before that, right? And here we can almost imagine that we added 2 before that. And here we can almost imagine that we added 5 before that. So if we now look at the toothpicks that are not highlighted, so in the diamond, we have 0 highlighted toothpicks. In the square, we have 1 highlighted toothpick. In the triangle, we have 1 highlighted toothpick. And in the hexagon, we have 1 highlighted toothpick. Well, where's the connection there? Looking at the rules, you should see that the square, the hexagon, and the triangle all have a +1. The diamond doesn't. There's nothing to add for the diamond. All the toothpicks come from the 4 end, 4 each time. Well, 3 each time for the square leaves 1 left over kind of at the beginning. And all of them kind of turn out that. So I'm going to call them non-highlighted for a second. Non-highlighted. But I'm going to also, can I give them another name? Non-highlighted, or perhaps original toothpicks. If you kind of think of the ones that they were not added, they were there before. The non-highlighted or original toothpicks are the constant in each rule. Okay, so let's look at our tables and more specifically the column for the number of toothpicks. What is the connection between the numbers in that column and the rules you listed in question 1? So this is where you kind of have to flip back and forth, but so let's do that real quick. Let's flip back over to here, and we were talking about this even as we were doing our rules here, is that you should be seeing that we have this +4 here, and we have in our formula a +4. We have a +5, and we have a 5 in our formula. We didn't write it here, of course, figures. We are going up by 2 here, 2 each time, and what do we have? A +2 in our formula. Oops. And even though we don't see exactly this 1, we know that the coefficient, when there's no coefficient written, is a 1. So we're seeing, and let's go back down to the diamond, oh, yeah, +4 here, +4 here. We know there's the same for the total. +2 here for square. We see 2 2's here, so it could be a little bit confusing, but it is the coefficient we're kind of looking at here. So +3, +3. Oof. Okay, so let's flip back over to where we were answering. Wish it would not do that. Okay, so what's the connection? What's happening? We could say, maybe it'd be even faster if I just typed it here. The column is increasing by the same number as the coefficient of our rules. And we even kind of talked about that a little bit when we were doing the ratio tables back before 2018, back in 2017. So things to think about, things to remember as well. Okay, so if you look again at your table and look for a connection between the constant in your table in the equation of the pattern. I'll leave that for you. We could talk about that maybe later, but there is a relationship to it. It says you may need to extend the pattern. Hint, hint, hint. So I'll leave that one for you to continue to think about. Okay, so on the back then it asks us to make a graph with the 4 tables for the total toothpicks. Again, we're sticking with the total. Look at the tables before you're choosing your scale. Okay, so here, if I scroll down, this is a graph of the 4 here. The triangle is made with triangles, the square with squares, the diamond with diamonds, and I couldn't make a hexagon shape, so it's just the X here. So we can see the 4 graphs here, and maybe you're noticing something. You might be noticing a couple of things, but as you look at them, you might remember something about the last time we were graphing things on a coordinate plane like this. So we see multiple things graphed all together. So if we come back here, should you connect the data points on your graph with a line? It's an interesting question. So we talked about that if we have a line that would be connecting them, a line is really like an infinite number of tiny little points. So if there was a point here, point, and there's points between the points, and so many points that eventually they string together and form an entire line. That's what a line means, is that there's points in between. So the question is, are there points in between? So what are we graphing? So train 4, train 5, train 4.5, is that something that we could actually make? Maybe we could be breaking toothpicks in half, but I don't think train 4.5 makes sense, or train 2.2 makes sense. So no, because there cannot be, I guess, fractions of trains, not by the pattern that we see following. Okay, so to make a train, you have to add a whole nother car of the train, so to speak. We'll come back to this, but there's a word for when we don't want to connect the points, when we want to just talk about there's individual values, and this data is called discrete data. So discrete data is individual points. Can't be connected. So we'll talk more about that as we go, but that is the word for it. We really should connect the dots for this graph. So even though we're not making a connected line, which geometry train made the line, the pattern with the steepest hill? So if we were going to rank them by their steepness, so let's go back and look here. Okay, hexagon, the steepest, way up here. Diamond, then square, then triangle. Okay, let's see if I can remember that. All right, so hexagon first is the steepest, and then diamond, and then square, and then triangle. Okay, so that's from looking at the graph. That's the steepnesses in order. Okay, so look again at each rule you listed in question 1. How do your 4 rules suggest the same order? So I'll write them here. The rules were, well, let me just put them in a random order. Okay, so I'll put them in this order. They were 4n, 2n plus 1, 3n plus 1, and 5n plus 1. Okay, so to kind of match them, this is the diamond, this is the triangle, this is the square, and this is the hexagon. So the hexagon was the steepest. The triangle was the least steep. Okay, so I'm looking at them, looking for something in the formula that would indicate that steepness. Well, hexagon's steepest, it has the biggest coefficient. Triangle, the least steep, has the lowest coefficient. And let's think that does it continue. Diamond, second steepest, and 4 is the second biggest coefficient, and then square is the third. So what about them suggests the same order? We could say that the coefficients are in the same order as the steepness of the lines. Very interesting to see that the coefficients are telling us again some important information about our data. Okay, so the constant is also related to your graph. Again, that's another challenge. I'm going to leave that up to you. Hint, a straight edge might help. Interesting. Continue to think about that. Okay, so this might be a place where you get to take down notes about this, but if you do get a little bit further, the next lesson to look at is, let's see, this page. Okay, so it's a little bit of a recap of what we've said here, and it's kind of setting us up to make some connections going forward. So in this equation, let's make sure we know these terms inside and out. The 5 here is the coefficient, and the 1 here is what we call a constant. Okay, so as we look at the number of the train, as the number increases here by just 1, so here going up 1 each time, the number of toothpicks also increases, but it increases by 5. So we're seeing that as one goes up by 1, the other's going up by 5. Great. And the following equation and table represent the same data. So let's answer some questions. How is the number 3 from the equation on the right important to the table on the left? So the 3, again, I'm going to type this. The 3 from the equation is the amount that the number of toothpicks, which we could also call that the dependent variable, is increasing by every time the train increases by 1. So we might see patterns later where the independent variable increases by more than 1 each time. And so it is kind of important to note that 3 here, this coefficient, is how much it changes by every time the train goes up by just 1. Okay. Again, think about the 2. The 2 is a challenge. How is that connected? So I'll leave that again for more thought. Okay, so why are the data points not connected here? So the data points are not connected because there are not values for trains that are fractional. The data is called discrete data, meaning that there are individual points that cannot be broken into pieces. So in class we'll talk about some other types of data that is typically discrete. People are discrete data. We don't generally talk about parts of people when we have data, so that would be another thing. But the opposite of discrete data, we'll just kind of throw this in there as a little note to self for other times, is continuous data. And continuous data is data that can be broken down and should be connected. And the number one example for continuous data is time. there's always half seconds and milliseconds, and time is a continuum, and it goes on, and we can always look at a smaller unit of time, whether we can measure it accurately or not. It's continuous data. So what type of data is appropriate? I should have read it. Is appropriate for us to connect our points. I didn't realize that was the next one. Okay, so continuous data is data that should be connected and can be divided into smaller and smaller pieces. Time is perhaps the most common example of continuous data. Okay, so let's play a super fun matching game here. So if we were to match the trains with the graphs here, so train A here is the blue, and so even if these are not necessarily the formulas from our trains, these are new trains that could exist out there, but we can still connect them because we know something about them. So train A is the third steepest, so it's going to be the third biggest coefficient. So 5 is the biggest, 4th next, then 3. So train A must be the 3n plus 3 equation. Train B, that's the square, that's the steepest one, so he's got to be the 5n plus 1. Train C, let's see, train C is the triangles, that's the least steep equation, so that's going to be 2n plus 4. And train D is obviously the one that's left over, but it's going to be the x's, which is the second steepest, which is 4n plus 2. So again, new formulas, new equations, we can match them here based off of the coefficients to see which one is the steepest. So that's again what we just said. We can match the graph to the equation by looking at the steepness of the graph and matching it to the highest value of the coefficient, and so forth. Okay, so let's look at, for the square train, we found 2 different formulas. Some of us might have, at least this person did. So are they equal to each other? So sometimes you'll see mathematicians put a question mark over the equal as something that's yet to be determined. So on the right hand side, 3n plus 1, we're going to leave that intact. And we're not going to try to solve this. We're just going to try to simplify it, and we're not going to even mess with this side over here, because this is like one side that we know. We want to see if the other side is the same. So on the other side, let's use the distributive property to get 3n minus 3. Multiply, multiply. Great. So we still have 3n plus 1. Is it equal to? Well, we have a 4 and a minus 3. So we can combine those. 4 and negative 3 is positive 1. Oh, so now we can conclude that they're the same. So we can conclude they're the same by trying to use the distributive property, other tools that we have to make them similar. So I'm going to stop here, and I think at this point you certainly could carry out and see if these other formulas are equivalent on this worksheet. And if you get this far, that's great. And we will talk more when I see you back in class.